Hello, class. Welcome back. Today is lecture 13, and we are going to be doing more applications, but really just a bunch of problems involving springs. So last time we saw that this is the differential equation telling us the position of the spring at any time t if there is air resistance and if there is a external force. But last time we said, like, what happens if there's no air resistance, so we made this 0, and no external force, we made this 0. This time we're going to bring everything in. So let's get started. Okay, so here is the first problem. 10 kilogram mass is attached to a spring stretching at 0.7 meters from natural length. The mass is started in motion from equilibrium with initial velocity 1 meter per second upward. Find the motion of force due to air resistance is negative 90 p prime newtons. So last time we used American units, I guess, or maybe they're called imperial units, and today we're using metric units instead. I'm never going to make you convert back and forth, so don't worry about that. Okay, so today this one is just metric, and that's it. All right, so how do we get started? Well, this is going to tell us K because it's telling us a force is stretching it from natural length, and we can use that to determine K. This is going to be telling us our initial conditions because it's saying how the motion will get started. And then air resistance, luckily we don't have to really figure anything out, it's just given to us right there. Okay, so how do we get started? First thing we're going to do is we're going to use Hooke's law again to get K. A little different than last time. Last time we're given the weight, which is the force. Now we're given the mass, but we can still use that. So the idea is that the force of gravity is what's causing this 0.7 meter stretch. And that means that the restoring force is equal and opposite to the force of gravity. So it's negative because gravity is positive, because down is positive. And that's going to equal to negative K times the length that it stretches because of that force, which is 0.7. And what's the force of gravity going to be? Well, the mass is 10, and the gravitational constant in metric units is 9.8. So this is negative 10 times 9.8. So that's going to be 98 divided by 0.7 is going to give us K. The negatives will cancel. And so K will be, this will be 140 if you plug this into your calculator. Great. So this is going to tell us K. The air resistance we're just given is negative 90 P prime. So that tells us B is 90. This N here is newtons. It's a unit of measure. It's not part of the equation or anything. Okay, and then there's still no external force mentioned, so that's still going to be 0, one step at a time. So all of this is just to set up the differential equation. So now it's going to be P double prime plus, so 90 is B over M is 10. K we just figured out is 140 over 10. It's the mass and the external force, so that's 0. Okay, so now we're down to a linear differential equation. Oops, it should just become 9 with constant coefficients, which we can solve using the characteristic equation. Lots of practice doing this. And this one I've made nice and easy to factor. So it's going to be lambda plus 7, lambda plus 2 equals 0. So the equation of motion is C1e to the negative 7, sorry, to the positive, no, negative 7. This is why you shouldn't skip steps. So that means lambda equals negative 7 and negative 2 are the solutions to the characteristic equation. So that means negative 7t plus c2e to the negative 2t gives us our position function. Great. So now we can use the initial conditions. So the question says that it's going to be started from motion, started from equilibrium. So the position is at 0. I'm not stretching it up or down to make it start. All I'm doing is giving it an initial velocity upward. Upward is negative. So I'm just tapping the spring to make it go upward. And that's how I'm getting it started. But the position is starting at is equilibrium. Velocity is -1 because it's starting upward. And I use these to find C1 and C2. So this is usually the most time-consuming part of these problems, is finding these constants, but I'll do it anyway. Okay, so 0 equals C1 e to the 0 plus C2 e to the 0. 0 equals C1 plus C2. So C1 equals negative C2. Great, that's what one equation tells us. The other one tells us that, well, at first I need the derivative. It's going to be negative 7C1e to negative 7t minus 2C2e to the negative 2t. So then I can say that -1 equals negative 7C1e to the 0 minus 2C2e to the 0. -1 equals negative 7C1 minus 2C2. And then I can use this over here. So I'll change C1 into negative C2. And then I'll be able to solve. Lots of algebra to not mess up. So just be very careful. And then what do we get here? 1/5, -1/5. Because that adds up to 5, and then you divide by 5. Great. That means that C1 is 1/5 because of this up here. So my final answer is going to be 1/5 e to the negative 7t minus 1/5 e to the negative 2t. Great. One thing you should do is try to analyze this and see if it intuitively makes sense for the setup. So what's going on is that the position decays to equilibrium very quickly. That's because there's a high amount of air resistance. It could be some other type of resistance, but I'm just keep using air, but it could be something else causing this resistance, like it's in water or something. But there's very high air resistance. And so the spring should very quickly go towards equilibrium. And that's exactly what the position function is saying, because this goes towards 0 as time goes on forever, but it does it very quickly. So these powers are negative, so they rapidly go towards 0 because they're exponential when time goes on. And so the graph of the position function will look something like this. Because I'm starting it by giving it initial velocity upward, the position goes up, which in the graph is down because we made up be negative, and then it'll very quickly just come back down towards equilibrium. And it won't go bounce back and forth or anything like that, like we saw last time. Okay, good. So then let's do another one. So let me pause while I write it down to save some time. Okay, so here is the problem. A mass of 1/4 kilogram is attached to a spring having spring constant 2 newtons per meter. So here, obviously I got lazy, and we're not gonna have to use Hooke's law. We're just gonna immediately know that this is K. And then we set it in motion in these ways. And so that's gonna be the initial conditions. And here is the air resistance. Okay, so let's get started. The idea is that we should just write everything down that we need. to make it work nice and easy. So what's the mass? The mass is 1/4. The spring constant we don't have to figure out this time, it's just 2. The air resistance tells us that B is 1. And there's no external force still, so that's still 0. Put it all together. Make a nice piping hot differential equation to solve. So 1 is B, so it's 1/1/4. P prime. K is 2 over the mass is 1/4. P, still no external force. So we get this. Okay, so this one's going to be a little bit differently, work a little differently. The idea is that the air resistance is so low that something a bit more interesting happens than last time. And let's see how that's reflected in our solution. All right, so we solve with the characteristic equation. The difference is that this time we can't factor it. We're going to have to use the quadratic formula to solve for lambda. So negative b plus or minus the square root of b squared is 16 minus 4 times 8 is 32. So skipping some steps because this is going to be a long video. So this is negative 16 over 2. So now we see that we're going to get some imaginary numbers. Plus or minus 4i over 2. So we get negative 2 plus or minus 2i. So what does that mean our solution looks like? The idea is that this thing we called A and this thing we called B. And then the solution was e to the negative 2 negative AT times C1 cosine of BT plus C2 sine of BT. So that's the solution. And this is a more interesting position function because what's going on is that this term will eventually make it decay to 0, make the position go towards 0, towards equilibrium. But this other stuff is saying that while it's going to 0, it'll oscillate. Whoops, oscillate. I don't know how to spell. Close enough. Okay, but we still got to do the initial conditions to find C1 and C2. So the initial condition said that I'm going to take the spring and I'm going to bring it down 2 meters. So that's telling me P of 0 is 2. But I'm also going to give it initial velocity 2 meters per second upward. So that's telling me that P prime is negative 2 at time 0. Okay, so let's see, plug this one in first. So this is telling me that 2 equals e to the 0 times C1 cosine of 0 plus C2 sine of 0. Luckily, sine of 0 is 0. So this just becomes C1 times cosine of 0, but cosine of 0 is 1. So we immediately get C1. Now to use the P prime, I need the derivative, which is going to use the product rule. It's not as bad as it looks. We can do it very quickly. Derivative of the first one, keep this one the same. Okay, then add, keep the first one the same. Take the derivative of cosine is negative sine. Oops, there should still be a C1 there. And then derivative of sine is cosine. C2. So now I plug 0 into this and set it equal to negative 2. So e to the 0 gets me 1. This becomes C1 plus 0 because sine of 0 is 0 plus e to the 0 is 1 times negative 2 times sine of 0 is 0 plus 2. C1 cosine of 0 is 1. C1 I already know is 2. So why don't I just plug that in? Oops, that's a C2, sorry. So what is this? So this is the hard part, negative 2 plus 4 equals 2C2, 2 equals 2C2, C2 equals 1. Great. So P of t is e to the negative 2t times C1 was 2 and C1 was 1. Or sorry, C2 was 1. Don't even have to write the 1. Sine of 2t. Okay, so if you graph this, it will look like something like this. So I'm starting off my position in the downward direction at 2 meters. So it's going to start at 2. And then I'm going to push it upward, which is downward. So I'm pushing it towards equilibrium. And then it's just going to bounce back and forth a bit while shrinking in amplitude until eventually it sort of just peters out. And that's makes sense because this time the resistance isn't that strong. So it just slowly weakens the amplitude instead of immediately making it go to equilibrium. This time it's allowed to bounce back and forth. Okay, so it decays to equilibrium while oscillating. This is because the air resistance is very low. This is what would happen in air. The previous one would probably happen instead of air resistance if it was like water resistance or something. If you had your spring in water, maybe it would very quickly go back to equilibrium because there's so much resistance from the water, whereas in air, it probably would do something like this. I keep calling it air resistance, but it could be anything. Okay, so that's that. Let's see, ready for the next one? Yes, let me pause again. Okay, so here is the next problem. Again, a 10 kilogram mass is attached to a spring and the spring constant will be 140. You should recognize that as something we got earlier in the first problem. And then here are our initial conditions. We're starting it from equilibrium with initial velocity at 1 meter per second upward. This time, what's new is there's an external force and there's air resistance again. So what is the differential equation describing the situation? It's going to be a little bit different. So I still know mass is 10, K is 140, B is 90. This time there is an external force. And so the differential equation is going to be P double prime plus 90 over 10 P prime plus 140 over 10 P. This time not equal to 0, but 5 sine of T, which we can reduce a little bit. So the left side should look very similar. Made it the same on purpose so we could do it very quickly. But now what we have is a non-homogeneous equation. And so how do we solve this? So first we get the complementary solution. Which I guess would be called P sub C instead of Y sub C. And so that just comes from setting the left side equal to 0. So we are experts at that. We already did that earlier. So I'm not going to redo it. It's just C1 e to the negative 7t plus C2 e to the negative 2t. So that's my complementary solution. So now what's different is I have to get a particular solution. So I guess that would be P sub P. And so we use the method of undetermined coefficients. So what we do is we guess a form based on the right side. So because it's a sine and derivative of sine gives you cosine and vice versa, our guess is A sine of t plus b cosine of t. And then we take derivatives so we can plug them all in. Oops, that's incorrect. This should be the minus one. Okay, now we're good. Pros at taking derivatives by now, minus b cosine of t. Plug these in and then solve for a and b. Be right back, 1 second. Okay, I am back. Whoops. Too long. Okay. So we're plugging these guys in to our differential equation. So let's see. So y double prime becomes this thing. And then plus 9 of y prime, or p prime, I guess. So lots of potential for algebra mistakes. There's lots going on here. Plus 14 a sine of t plus b cosine of t. That all needs to add up to the, oh, I made a little typo at the beginning. This 5 is incorrect. It's supposed to be 5. It's a common mistake, and I made it. It's the force. The force should also be divided by the mass here. So this should also be divided by 10. So this should be half a sine of t. Common mistake, and I just did it. All right. Okay, so that needs to add up to that. We got this giant equation. All we're going to do is put common terms together. So put all the signs together. So there's a negative a sign there, plus 9 more a. Oh, sorry. If I distribute this in here, there's a negative 9b next to the sign. And then if I distribute that there, there's another 14 a's. So that's how many signs there should be. How many cosines should there be? There's a negative b, and then there's a 9a of them, and a 14b of them. Oops. So method of undetermined coefficients can take a while. All right, so but we're on the right path now. So what is this? This is 13. Oops, that's a 19. There are 13 A's minus 9 B's. That needs to equal a half because there's that many signs. And then there's 9 A's plus 13 B's that need to add up to 0 cosines. So here we can solve for A in terms of B and get this. And then we could plug that in there. So systems of equations take a while, but we can do it. And I don't want to show all the messy algebra. It's embarrassing to do in front of people. So I'll just pretend that I did it all perfectly. And then I got to here. And then B will be negative 9 over 500. Plug that in there. And A will be 13 over 500. So we have our particular solution by plugging A and B back in. And then we have our general solution by combining it with the complementary solution. So here I'm plugging A and B back in to our guess. So that is where I'm plugging that in. That's my particular solution. Then I add that to my original complementary solution. And now I need to use the initial conditions. But before that, we can already analyze what's going on. So the idea is that these two terms, just like before, they will go away. They'll go towards zero as time goes to infinity. And so that's like the natural motion of the spring. So the idea is that the air resistance causes the natural motion of the spring to disappear, and then the external force sort of takes over. So that came from the external force, and it's saying like, okay, the natural spring motion will stop, but then the external force takes over. Okay, so anyway, we can finish the problem now with initial conditions. So we're starting at equilibrium, and we are sending it upward with 1 meter per second. And I don't want to do all this work, so I'm just going to tell you what you should get. C1 is 99 over 500, and C2 is negative 90 over 500. So it takes a lot of annoying work to do that, but can be done. Okay, but this is what you'll get. And then you just plug these back in. I've got too much to do for me to show you all the algebra, fortunately, but that's okay. So that's that one. So then we can sort of picture the graph as well. And it's going to just be it's not decaying anymore. It's pretty much just going to look like sine and cosine, because what's happening is the natural spring motion is decaying away towards zero as time goes on, but it's not getting rid of the rest. The rest is here. It's not being multiplied by zero. It's just here. So it's sort of just going to oscillate. And this is because of the external force being a sine function. It just causes the position to follow along with the external force. So the idea here is like in this situation, what's going on is maybe somebody is like grabbing the thing and they're just pushing, and they're just like pushing it up and down, up and down. So here's my moving picture of the situation. So some guy's just grabbing onto the board that's holding the spring and just pushing it up and down, up and down. That would be like an external force acting on the spring and doing it in this pattern of sine. So eventually the motion of the spring just becomes the motion of the external force once the air resistance has stopped the natural motion of the spring. Okay, so now what I would like to do is just summarize all the situations that could happen. So let's do that. There's lots of things that can happen, and it's hard to do every possible example. So let's just summarize the possibilities. All right, so we're gonna have, first of all, we're gonna break it into 3 cases, but the first case will actually have 3 sub cases. So the first case is, what if there is no external force? So we've seen that. And when that happens, lots of different things can happen depending on the air resistance. So let's say that there is air resistance. So B is not just 0. Then the differential equation will look something like this. Which we can solve by using the characteristic equation. So lambda squared plus B over M lambda plus K for M equals 0. And we can solve for lambda using the quadratic formula. And then this can tell us all the possibilities once we have this. So we're going to use the quadratic formula here. It'll be negative b over m plus or minus the square root of b over m squared minus 4a is 1 times k over m over 2. So let's just analyze what can happen here. So one thing to notice is that right off the bat, this is going to be a negative number because b and m are always negatives or positives. So then you have a negative positive. So this is a negative number no matter what. And also it's bigger than this piece no matter what. Why is that? It's because if I square something, if I square that exact same thing, which is what's going on there, but then I subtract a little bit. So I subtract something and then I square root it afterwards, it's going to get smaller than it originally was. That's the idea anyway. And is bigger than this thing. So the whole top is negative no matter what. Just to keep that in mind. So then there's going to be 3 subcases, like I said. So here's the first subcase. So it's going to depend on the inside of the square root. Depending on what happens there, we'll get 3 different subcases. So if this thing is positive, then you're just getting the square root of a positive number, nice and easy, and you do plus or minus that positive number, and so you get 2 solutions, 2 real number solutions. This is like the first example we did today. And they're both negative, as I said they would be. So then the solution function is always going to look like this in this situation. And the powers are negative, so it's going to go to 0 as time goes on to infinity. And this is the first situation, this is the first example we did, and this is called being overdamped. So when you have that the inside is positive of the square root, this is called being overdamped, and it's because there's too much air resistance or too much resistance of whatever kind. And so the graphs of these kinds of solutions always look something like they just decay directly to equilibrium. Sometimes they could like go up a bit and then decay. Stuff like that can happen too. Or from down here. So you should use different colors for each one. They usually look like one of these variations. So the spring doesn't oscillate at all because it just decays very quickly. And it's because this inside is positive. So it's good to think about, when will this be positive? Well, that depends on this guy being bigger, since you're subtracting, than this guy. So it's good to think about when that might happen. Okay, so the next case is that it equals exactly 0. So if you end up with the inside of the square root being exactly 0, we didn't have an example of this one today, then what's going to happen is you're going to have a repeated root. So your solution is going to be C1e to that root, but then you have to add a t in here, multiply a t in here on the next one to get the solution. So that's going to be when, again, when this equals 0, And that's because in the quadratic formula, if you go up to the quadratic formula, way over here, you're doing a plus or minus 0, which is just the same. They're both the same. So you're just getting this thing as your answer twice. So it's a repeated 0, a repeated real number solution. And so that, remember that when you get that this is the solution to the differential equation. And it looks very much like the previous one. This is called being critically damped. Because it's like right on the edge. If it was just a little bit bigger, instead of being 0, it would be over damped again. And if it was a little bit less, then we'll see what happens next. So there's still really no oscillation in the graph. There's like a little bit, but it basically looks the same, except sometimes it might go past, but it could also do this in the first case too, and then come back to equilibrium. But sometimes it might not. It could also just go straight to equilibrium, like the previous one did, depending on the initial conditions. And it could do that from up here too. Or from down there. Just depends on the initial conditions. Okay. And then lastly, the third subcase is when the inside of the square root is negative. So then you get imaginary numbers. I guess B is already taken, so I'm not going to do A plus BI. I'm going to do alpha plus beta I. That's okay. So these are your two solutions. And remember that what that means is your solution to the differential equation is e to the alpha t. Usually we called it A, but I don't want to use B because B is already taken in for air resistance. And then it was cosine of beta t. And then sine of beta t. And alpha is always going to be negative. As I said earlier, that's the B over M part in the front of the quadratic formula, way back here. That's this thing. This is going to be your alpha there. And that's always going to be negative. So no matter what, in these spring problems, this thing will go towards 0 as time goes on, because it's a negative exponent of an exponential. It'll shrink towards 0, causing the whole function to shrink towards 0 because it's being multiplied to this other piece, which is it just oscillating. So this will cause an oscillation. So the whole thing will go towards 0, but as it's going towards 0, depending on the initial conditions, it might do something like this. As it's going towards 0, it's going back and forth about 0 forever. So it could look like that, but the initial conditions could make it start down here maybe instead. And then it could do the same thing, but down here. And that's the idea. So this is called oscillatory damped. So it decays towards 0 as it's oscillating about 0. Okay, so all of these in this entire case are also called transient motion. So more fancy terminology. And that just means they die out. So in all three situations of case 1, they die out, they go towards 0 eventually as time goes on. But in the next case, that doesn't happen. This is the case we saw yesterday. So now we're on case 2, which is if there's no external force and no air resistance, then you're just going to get P double prime plus K over MP equals 0. And because K and M are both positive, when you subtract it over and you solve, you're going to get two imaginary numbers. But the real part, there's no real part of this imaginary number, so it's going to always be 0 plus or minus some beta I, instead of being like 5 plus or minus beta I, it's always going to be 0. So the position function will look like e to the 0 t times c1 cosine of beta t plus c2 sine of beta t. And so that 0 t here means that the exponential is not going to be there to cause it to go to 0. So this one, it doesn't go to 0, and that makes sense because there's no air resistance decaying the motion as it continues. So it just does not go to 0. And there's no air resistance, and it's called steady state motion. So it does not die out. It just oscillates back and forth forever. And then the third case is if there is an external force. Well, there's too many things can happen. So we can't really break it down. But in most situations, the position function eventually follows the force, that's the external force, as time goes on, which is what we saw in our one example today. But other things can happen, weirder things can happen. And you'll see that in the lecture problems, something called pure resonance. Okay, so that's it for today. See you next time.